Alright, today we're going to talk about ecological succession. So our standard says, obtain, evaluate, and communicate information to construct explanations of stability and change in Earth's ecosystems. Construct an argument to predict changes in biomass, biodiversity, and complexity within ecosystems in terms of ecological succession. Our learning goal is to predict changes in biomass, biodiversity, and complexity within ecosystems in terms of ecological succession, define biomass, biodiversity, complexity, and ecological succession, identify types of ecological succession, and explain how the types of succession affects biomass, biodiversity, and complexity in an ecosystem. So first, let's watch a short video.
Mount St. Helens in Washington State is one of the most well-monitored volcanoes on the planet, and with good reason. It is still active, and more than 3 decades to the day after it launched a stunning and destructive display of lava and ash, it continues to transform a region and its ecology. Even now, scientists are still learning about the aftermath and how some life is emerging from the ashes. Science correspondent Miles O'Brien has the story, part of our new weekly series about exploring the leading edge of science.
36 years after its spectacular, deadly eruption, Mount St. Helens still rumbles and bears scars from that earth-shattering day. But hike down the slopes, away from the jagged crater just a little, and you'll see Mother Nature hard at work. And there's a good chance you'll bump into a team of scientists led by John Bishop. He is an evolutionary biologist at Washington State University, Vancouver.
The goal of our research is to understand how plant and animal communities reform after a catastrophic disturbance.
Bishop is one of a select group of researchers studying this rebound from a volcanic eruption. Back in 1980, Mount St. Helens had given scientists all kinds of clues that a big disturbance was brewing. 2 months before it blew, the volcano was venting huge amounts of steam, and there was a series of earthquakes. Even with all those ominous signs, the eruption was larger than anyone predicted. It happened at 8:32 on the morning of May 18, 1980. An earthquake caused the north face of the mountain to collapse.
After that, it uncorked an explosion that was directed horizontally and leveled the forest to 13 miles out from the volcano.
The eruption column of volcanic ash and gas rose 80,000 feet, while a tsunami of 1,800-degree gas and rock raced down the valley at 450 miles an hour, a so-called pyroclastic flow.
Anything biological that was remaining after the landslide would have been completely vaporized. It was just a barren landscape, gray and pumice-colored.
It killed every living thing in a 230-square-mile area. What was left was akin to a moonscape. 57 people died. Some remains were never recovered. Bishop and his team have had a front-row seat as nature got busy bringing this place back to life. They wanted to know where it begins and how it takes root. Here, it started with these purple flowers. Alpine lupin were the first plants to return. For many years, they were pretty much the only game in town. But as they went through their life cycles over several seasons, they created soil from the volcanic ash. And that made it possible for woody plants, like the Sitka willow, to find a home. They are how a forest gets started, but it hasn't been easy for them.
One of the things we've realized about these willows is that they're not getting big. That's important because they create habitat for birds and mammals. We've learned that these landscapes are characterized by extreme instability in the populations of the plants and animals that colonize them.
In a recovering ecosystem like this one, where just a few species have managed to regain a toehold, even seemingly insignificant pests can play an outsized role in how the landscape bounces back. These weevils are an invasive species with a particular taste for the Sitka willow.
Any stem larger than about 1 centimeter is usually destroyed by this weevil. And the effect of it is to keep these plants small, not let them form the architecture that's needed for bird and mammal habitat.
But Bishop says it's important to remember we're still early on in what will be a very long game. He says the plants and insects will battle it out over time, and eventually the ecosystem will become more diverse, more stable, and this will be a forest again.
When I'm out there working on the pumice plain, one moment I'll look around and I'll be stunned by the amount of vegetation and the number of birds that are present. But then the next moment I step back and I think, there is hardly anything here. We're centuries away from replacing the old-growth forest that was there.
Mount St. Helens is the perfect place to test an important question in ecology. Life does go on, but how? John Bishop will keep looking for the answer here, unless Mount St. Helens awakens and reboots the landscape once again. Miles O'Brien, the PBS NewsHour.
All right, so there are some key terms that we need to define, and you guys need to be writing this information in your notes, taking notes. Biomass. So what is biomass? So biomass describes the amount of organic material in an ecosystem. Producers add biomass to an ecosystem by making organic compounds. All right, so here we see corn growing and an apple tree, and so that's all types of biomass. What is biodiversity? So all the variety of life that can be found on Earth, the plants, the animals, the fungi, and the microorganisms, as well as the communities that they form and the habitats in which they live, that's all relative to biodiversity. And so in the video, you noticed that they were talking about the lack of biodiversity after the eruption of Mount St. Helens. And the reason for that is it killed everything, and so nothing was able to live for a while. And then plants started coming back. And there was very little biodiversity in that area. There's only couple of types of plants that were growing, and very few animals that were able to survive there. They were talking about over time how as more and more plants are able to survive there, then it should also be able to sustain more and more animal types. And so the biodiversity is predicted to increase over time in that area as more plants are able to survive there. Complexity. So complexity basically means exactly what you probably think it means. Okay, so it has many parts, it's complicated or intricate. So to predict changes in complexity of an ecosystem is to predict changes in its parts. So complexity is a term in ecology that is often used in different ways to describe the state of an ecosystem. Ecological complexity has been linked to concepts such as ecological integrity, diversity, and resilience. So here's some examples here. Communities are always changing, usually from simple to more complex, in a process called ecological succession. All right, so if you think back to that video, before Mount St. Helens erupted, you had this really complicated forest there, supporting lots of plants, animals, and so when we talk about complexity in terms of the ecosystem, we're talking about ecological succession being this sort of gradual change to where you go from simple to more complex, and more complex to really, really complicated. And so it's sort of this evolution of sorts of the ecosystem. So succession is not affected by seasons and is relatively orderly in repeatable series of changes in the types of species which occupy a given area through time. So it often begins with unstable, immature communities, pioneering species, opportunistic, and strategists, and proceeds to more mature, stable communities dominated by a case strategist. Okay, so we'll talk about that in the next slide here. Ecological succession. So again, what is ecological succession? It's the gradual process by which ecosystems change and develop or recover over time. Nothing remains the same, and habitats are constantly changing. Okay, so we talked about it in the video, and we're talking about ecological succession. They were talking about how eventually those plants they're going to have a larger number of plants. And eventually it will end up being a forest, but it takes a long time in order to get to that point. But that process is called ecological succession. All right, so there are two types of succession, primary and secondary. So when you talk about biomass, remember biomass is anything within an ecosystem. Okay, any organic matter that's in the ecosystem. So biomass is at maximum in the undisturbed ecosystem and increases up to this maximum during succession. Plant productivity also grows, especially if the plant cover was destroyed substantially by disturbance. So when we talk about biomass, you have a large amount of biomass in a forest compared to in a desert, right? Because you have all these different types of plants and animals, fungi, and bacteria, all these things that contribute to the biomass in a forest compared to that in a desert. All right, so let's go through the process of ecological succession. So when we talk about biodiversity, so that would be the number of species within an area. So biodiversity is actually measured as number of species having a substantial population density is lower in the undisturbed ecosystem than in the disturbed one. So at the very beginning of succession, you have a very low biodiversity. Okay, and at the very end of ecological succession, you have a very high biodiversity. So we see that process here. So in primary succession, we're starting out with bare rock, okay? And you have this amount of time where you have these pioneer species that are sort of starting to inhabit this area. So you start out with bare rock, and then you have lichens that start to grow upon the rock. And then you have small annual plants that start to grow, okay? And then, of course, you still have the lichens. And then eventually you start to have grasses and perennials. Okay, perennials are plants that come back every year. Lilies are an example of a perennial plant where you plant a bulb and every year the lily will come back and grow. All right, so you have this time in primary succession where you have pioneer species, and then you have this time where you have intermediate species, grasses, shrubs, and shade-intolerant trees such as pine trees. Okay, and then you have a climax community where you have shade-tolerant trees such as oak and hickory trees. So succession progresses from pioneer species to more complex ecosystems and longer-lived trees, ultimately resulting in a climax community where you have more shade-tolerant trees such as oak and hickory trees. So succession often involves a progression from communities with lower species diversity, which may be less stable, to communities with higher species diversity, which may be more stable typically. So complexity increases throughout the stages of ecological succession. Beginning of succession is low, and the end of succession is higher complexity. here in primary succession, newly exposed or newly formed rocks is colonized by living things for the first time. Again, you can see this figure closer up. So you have this amount of time where you have these pioneer species. You're starting out with bare rock, and then you have lichens that start to grow in the bare rock, and then you also have small annual plants that start to grow, and then grasses and perennials, okay, and then intermediate species, grasses, shrubs, and shade intolerant trees such as pine trees start to grow. And then finally, in your climax community, you also have larger trees like oak trees and hickory trees that are more shade tolerant, and so you end up with, you're able to have a forest area there. Let's talk about pioneer species. So they appear early in ecological succession. So they are usually the first organisms to inhabit an area, to colonize an area. Okay. So some characteristics of pioneer species. They tend to be small. They grow very fast, and they're very fast at reproducing. Okay. That's something to remember about pioneer species. All right, so let's talk about some possible pioneer species. We talked about lichens being a pioneer species. And a lichen is cyanobacteria and fungi together make a lichen. So pioneer species are those organisms, usually plants, that colonize barren rock or lava during primary succession. So examples: lichens, mosses, ferns, weeds. Those are all examples of pioneer species. So pioneer species. These organisms have adaptations that make them well suited to invading and occupying a new area. For example, they may be very good at seed dispersal or have adaptations that allow them to withstand harsh conditions. We see here a lichen growing on a rock here. This looks like the rocks that are out in the stream. And here we see some weeds growing out where there's no other plant life there. All right, so what is a climax community? So the climax community is the community that we eventually get to. Okay, it's a stable community. It's the final result of ecological succession. It generally remains the same if undisturbed. Okay, so examples of climax communities depend on the ecosystem itself. A climax community for a desert is different from a tropical rainforest. So here we see a climax community for a desert. Here we see a forest. Both primary and secondary successions ends with a climax community. All right, so here again, a climax community is a stable group of plants and animals that is the end result of succession. Okay, and so you end up with a large forest with a very large biodiversity, very large number of different plants and animals, and fungi and bacteria that all are thriving in an area, in an ecosystem. So the organisms in each stage of ecological succession alter the physical environment in ways that make it less favorable for themselves, but more favorable for the organisms that follow. The climax community remains constant for a long period of time, and it will stay that way forever if allowed to.